So this is Van der Waals equation of state. P equals RT over V minus B minus A over V squared. So now, in order to calculate these A and B values, we can see from this graph that right here at the critical temperature, this line here, that the derivative of this will equal 0, as you can see from this flat curve. And also the second derivative will also equal 0 because it's changing from concave up to concave down. So next I will be taking the first derivative and second derivative of this and setting it equal to 0. So now I'm going to take the derivative of this, and it's going to be the partial derivative with respect to v. With respect to v equals, so it would be negative RT over v minus b squared, and then plus 2a over b to the third. And then now I'm going to do the second derivative, partial derivative with respect to v as well. That squared. So this time it will be 2 RT over v minus b to the third, and then minus 6a over v to the fourth. Now we can set these equal to 0 if they're at the critical temperature and volume. So this will be the critical volumes and then the critical temperatures. And this is also the critical volume. So now we have two equations and two unknowns that we can solve for. So I'm going to move this to the other side and get negative RTC over VC minus V squared equals negative, or actually I'm just going to move this one to the other side to get positive of both of these. So now 2a over bc to the third. And then our other one is going to be 2 RTC over vc minus b to the third equals 6a over bc to the fourth. So now to solve this, we can multiply by the inverse. So flip this and then multiply by these to get vc minus b over 2 equals, flip that, vc over 3. So now we can solve for b by cross multiplying. So 2 VC will equal 3 VC minus 3B. So now we can isolate B, and we will get that B will be equal to track 3, so negative VC equals negative 3B. So B will be equal to VC over 3. Now since we have B, we can plug it back in order to get our A. So I'm going to plug it into this one right here. So we get that R TC over 2/3 VC squared equals 2A over VC to the third. By plugging in, that's VC over 3 for B right here. So now we just need to solve this equation for A. So we can simplify this to 9 over 4 times RTC over VC squared, because all you're doing is just squaring these, and then that'll still equal 2A over VC to the third. And then now I am going to multiply this VC to the third over and divide everything by 2. So now A will equal 9 over 8, and then these VC's will cancel, so R TC VC. So now we have solved for our A and B in the van der Waals equation of state. So now I'm going to get the compressibility factor for the van der Waals equation of state. So the compressibility factor Z is equal to PV over RT. And for an ideal gas, it'll be equal to 1. But to find this for our van der Waals equation, we are going to have to plug in our A and B to the van der Waals equation at the critical pressure, temperature, and volume. So the critical pressure equals R times the critical temperature over critical volume minus B, which is the critical volume over 3. And then minus A, which is this. So 9 over 8 R critical temperature, critical volume, And then we still have this critical volume squared from the van der Waals equation. So now we can simplify this to the critical pressure equals, it'll be 3/2 times R times the critical temperature over the critical volume, and then minus 9/8 times R times the critical temperature over the critical volume. So now we can combine these and get the critical pressure is equal to R times the critical temperature over the critical volume times 12 minus 9/8. So this can be simplified to pressure equals R times critical temperature over the critical volume times 3/8. 3/8. So now if we just move this to the other side, then we will get the compressibility factor at the critical temperature will equal 3/8. And this compressibility factor of 3/8 at the critical temperature, pressure, and volume is true for any compound, because according to the van der Waals equation of state.